Hello guys, welcome back to my channel based on African motifs. So shall just have a continuation from the last part on our shear. So here we've got the part of shear that you're going to at least focus on. So I think the first part is clear, where you're going to work with the shear. That is, you're supposed to know the characteristics between the object and the image. So if you have to cross-check under shear, the object and the image, they are not the same. That is, if you have to cross-check what we had on translation, reflection and rotation, the object and the image, they were congruent, but this one, they are not the same. So that is what we are having under shear. We are saying the object and the image, they are not the same. That is the major important part. Okay. Then the other point that you're supposed to note is that when you are to join points this time from the object to the image, you are going to produce parallel lines. That is, the points, they are going to move parallel to the invariant line. Not to say you are going to have parallel lines, no, but when you join the points, they are going to meet, which are the parallel. Where they meet, they'll meet in either in the x-axis, which is your invariant line, or they can meet in the y-axis, which can be the invariant line. So once you have your invariant line, then you're supposed to know that these points, they move parallel to the invariant line. So I'll explain about how you're going to have this working on examples, but that is the first part that you're supposed to have. Let us see. Now, once you know this, then you're supposed to describe your shear. Then to describe a shear, we are saying you're going to state that it is a shear. You state the invariant line, that is the equation of the invariant line. So here, mostly it can be the x-axis or it can be the y-axis. So these are the invariant line that you're going to have, x-axis and the y-axis. Then also you state the shear factor. So the shear factor, I'm going to explain also on this part here. If you are to cross-check here, we are given to find the shear factor. Shear factor is simply the distance moved by a point over the distance of that point from the invariant line, which is the one that you started with, the invariant line, to locate the invariant line first. So this one we are going to explain using the example, but that is the formula for shear factor, the distance moved by a point over the distance of that point from the invariant line. All right, so I want us to check this part here. That is the matrices that you're going to use for shear. So according to the x-axis invariant, you're going to use, this is the matrix for shear, which is 10, K1, or you can just memorize using the mnemonics of log key there, that is log key L, that is 10, K1, which means I've got log key this way, or you can take your log key in a vice versa like this. That is for the y-axis like this one, log key this way. So this is the matrix that you're going to have, where this K is representing the shear factor. So if you're given a shear factor of 2, you are going to substitute 2 where you're given that shear factor. So that is the matrix that you're going to have. So it follows that, just as usual, your matrix here by the object should give you the image. So that one does not change. So which means the matrix that you're going to have multiplied by the object, you're going to obtain the coordinates of what? Of the image. So that is the idea for the matrix. So actually you're supposed to know these matrices, which is the for shear. You're going to see the difference on these matrices later on the stretch part, where you'll be working with stretch. Okay, so let us see the first example that we can be given. We are given to draw and label triangle ABC with vertices A minus 2, 4, B minus 4, 2, and that is C minus 4, 4. So you're going to plot the coordinates of the object using a suitable scale. So here I'm already having this, that is ABC. This is the scale, 2 centimeters, representing 2 units on both axes. So we've got our first triangle, which is ABC, and the second one, A1, B1, C1. Okay, so the question is for us to describe. Now, if you have to cross-check here, we are now asked on the question to describe fully. That one will be full. Actually, you have to describe everything fully here. So it will be described fully the single transformation, which means we are referring to one transformation that we're going to work with, which maps ABC onto triangle A1, B1, C1. Okay, so this is what is going to happen, guys. You check on your question. These are the things that you're supposed to cross-check. If we are to look at this question, we can't say this is enlargement, because if we are to cross-check on enlargement, we say all the sides, they will be increased. But here, if we are to cross-check from C to A, from C1 to A1, this side is still the same, it never changed. So which means already enlargement is out. The other thing that we are supposed to note, so we are saying here, enlargement is totally out. So enlargement, we can't talk about this at this moment. The moment that we can't refer to enlargement, it means also we can't refer to two-way stretch. Two-way stretch is also out here. And also all the isometries, they're also out. All those isometries, which means we are referring to what? We are referring to translation is out, rotation is out, reflection is out. So the only two transformations that we are left with is the shear or the one-way stretch. All right, so this is what I want you to actually note from this part. We're left with shear and one-way stretch. So from this part, we are going to see that from the points that we have, because these are the two answers that you're supposed to have, either shear or one-way stretch. How are we going to see that it's a shear or it's a one-way stretch? This is where I'm saying for shear, the points, they are going to move parallel to the invariant line. Sorry for that, I'm not supposed to have this page. I want you to see from this part here that we did on the description of on the shear part there, we said, okay, I want us to get the first page here. We said for shear, these points, they are going to move, that is from this part here, we are given that points move parallel to the invariant line. So this is what you need. You must find the invariant line, which is the x-axis or the y-axis. Then from there, you can tell that it is a shear or it is a one-way stretch. How are you going to tell that? Okay, this is what you're going to do from our question. I want us to join these points so that we can see if truly it is a shear or not. So you just join corresponding lines. It's like a continuation. The ones that are going to meet, it's not like all the lines, they are going to meet at a certain point. No, it's not like that. Yes, it can happen that they are going to meet all in the invariant line, but sometimes it's not like that. So you just join, like here, I'm going to join just a continuation, C and B, this one, BC, you just continue with that line. Okay, this is what I'm trying to say. Let me put a ruler here. Okay, so that you can see what is happening. All right. So I'm just going to make a continuation from the point B to C. So you just make a continuation from there, like this. Okay, so this is our B to C. Let us just make a continuation from here. We are going to have something of this nature. Okay, let us just even, we can make it the red one. Okay, so if we continue with this line, we just make a continuation with this line like this, okay? That is BC. We do the same on this one, B1 to C1. We want to see where they are going to meet, okay? B1 and C1. This is our B1, C1. So I'm just going to make a continuation from that line again. So you do not join like points, you continue the line as it is. All right, so if I continue this line, which is a C to C1, they are going to meet, as you can see, this is our C, our B to B1, like that. You do the same. So without waste of time, you can see that these two lines, B to B1, C to C1, they meet in the x-axis here. At this point -4, it's in the x-axis. So it means our invariant line is the x-axis. Where these two meet, they meet in the x-axis. So we are now guaranteed to say our x-axis is the invariant line. All right. From the invariant line, that is where now we are going to tell that this transformation is a shear or it's an enlarge, or it's a one-way stretch, I mean. Okay. So we said for shear, the points, they are going to move parallel to the invariant line. Okay. And we said our invariant line is the x-axis, this one. Okay. So let us just indicate, we said is the x-axis. So let us see how the points are being moved from each point to another. Okay, we've got the point A, which was moved A to A1. This is the movement A is moving this direction to A1. B is moving this direction to B1. As you can see, as A is moving to A1, B is moving to B1, C is moving. These lines that we are creating, they are parallel to the x-axis. As you can see, this is your x-axis. So these lines with the x-axis, as you are moving from A to you are having a horizontal line, and they are parallel. So which means that one is a shear, because we said shear points, they move parallel to the invariant line. So these points, according to the x-axis, which is the invariant line, they are parallel to the what? To the x-axis. So that means we can conclude to say that truly this is a shear. All right, so we are going to describe now. It is a what? It is a shear. So on your description, this is the first thing. It is a shear. All right, so already the invariant line is there. So x-axis invariant. So we've got x-axis invariant here. All right, then we need the shear factor. All right, so the shear factor is the one that I'm saying is the distance moved by a point over the distance of that point from the invariant line. So what are we trying to say? The distance moved by a point, we are saying, we are going to check. Let us start with A. A moved from this point where it is to A1. So you're going to take that distance with respect to the scale that you're given. As you can see, according to scale, each box is representing what? 2 units. So I'm going to start with A. So we said the shear factor is distance moved by a point. So A moved to A1 over distance of that point, which is the point A from the invariant line. Our invariant line is the x-axis. Okay, so let us start with the distance of A to A1. Okay, so this is A to A1 according to scale. It's going to be 2, 4, 6, 8. That is according to scale, it's 8. So distance moved by A to A1, it's 8 units. All right, so this one is 8 units over the distance of that point A from the invariant line, which is the x-axis invariant. Okay, so let us start from the x-axis invariant to point A. So we are starting, this is your x-axis, direct at this point to point. You are moving straight to the point A. So how many units from the x-axis? You're going to move to 4. So as you can see, it's 4 units to point A. Okay, so it's going to be over 4. So that means we are going to have 8 over 4, which is 2. But this must be common throughout. So you can use B to B1 as a proof, okay? B to B1 over the distance of B from the invariant line, okay, which is the x-axis invariant, okay? So let us count the boxes from B to B1. According to scale from B to B1, we have got 2, 4. This is according, we've got 2, 4. According to scale, these are 2 boxes, but they represent 4 according to scale. So it's 2, 4, okay? So we've got 4 units here, B to B1, that is 4 units over the distance of B from the invariant line, the point B from the invariant line. Okay, so we are saying this is our point B here. So B from the invariant line, as you can note, is 2 units. From the invariant line going to B is just 1 box, which is 2 units. So it's over 2. All right, so as you can see, we are obtaining the same answer, which is 2. So that is our shear factor, which is 2. So what you do is that you use one, you can prove with another one. You can also prove with C to C1. I want you to see it's going to give us the same answer. Let us take C to C1. So we're going to move C to C1 over the distance of C from the invariant line. Okay, so C to C1, let us cross check here on our diagram. That is C here to C1. Okay, so according to scale is 2, 4, 6, 8. These are 8 boxes. I mean 8 according to scale. So it's going to be 8 over the corresponding distance, which is C from the invariant line. Okay, so let us cross check our C from the invariant line. So from the invariant line, which is our x-axis, going to C is going to be 2, 4. Those are 4 boxes. I mean, according to scale, it's going to be 4. So if we divide these two, we are going to obtain the same answer, which is 2. So as you can see, we are having the same answer throughout, which is 2. So that means truly that is our shear factor. It can't be we are having a shear factor of 2. Another part gives you a shear factor of 3 or another number. It means that one is wrong. But in this case, as you can see, you're obtaining the same shear factor. So that's how you actually see that it's a shear. So the first thing on shear that you need to know is that you're going to have the invariant line. The invariant line is the one that you're going to use. From the invariant line, you're saying, I have got the x-axis as the invariant line. Then what is the movement of the points? Like the points when they are they moving parallel or it's perpendicular? So if they are parallel to the invariant line, that one is a shear. We are going to see the opposite now on the one-way stretch, which is going to move perpendicular to the invariant line. So these ones, they are moving in a parallel way. Okay, so that's it. I want us to cross-check another part here. I want us to see this question. This one is direct question. Actually, draw and label triangle ABC with the vertices. These are the vertices of triangle ABC. We have our triangle according to the scale. Okay, that's our ABC here. And the question is now, draw and label the image of ABC under a shear x-axis invariant with a shear factor 2. So remember, guys, if you're dealing with shear, whenever you're given a matrix, a shear factor, you're supposed to apply the matrix. At least it can actually help us. Okay, so let me just change this background here. All right, so I think like this is fine. So what you're going to do, we are going to take the matrix. This is for shear x-axis invariant. So remember our matrices, we said we've got two matrices for shear from the low-key concept. We've got this one, low-key like this, or we can have our low-key like this. Okay, so these are the two matrices that we have. But what is the best matrix that you're going to use? We are given that it's x-axis invariant, which means the x-axis is not moving. So this is the one, because remember, this is your xy, this is your xy. So x-axis is at 1, 0, which means it's not moving. So this is the matrix 1, 0, 1, 0, k, sorry, it's going to be like this, 1, 0, k, 1, where k is the shear factor. And we are given that the shear factor is -2. So our matrix is going to be like this, 1, 0. All right, so let me just write it here. So our matrix is going to be 1, 0, 2, 1. So that is the matrix that you're going to have. Remember your shear factor, okay, it's -2, this one, so it's going to be -2. But the concept does not change. Matrix times object should always give you the image. All right, so I'm just going to take these coordinates so that it can be easier for us. We are given the first part. I'm just going to take these coordinates so that it can be actually easier for us. Remember that the first part that we are given, A is -2, -2. So I'm just going to write these coordinates. Our A here, which is -2, -2. Our B was -4, -4. Our C was 0, -4. Okay, so these are the coordinates that you're going to have. So at this stage, guys, it's all about you and your multiplication. That is what you're having, row by column. I think it can actually help us. Okay, so performing matrix multiplication, we are going to have something like this nature. All right, so here using our row by column concept, we have got a row and versus the column here. So we are going to multiply, that's 1 by -2, which is -2 here, plus we move on -2 by -2, which is a +4. We are done with this part. Then we move on this row to this column. So it's 1 by -4, which is -4, plus -2 by -4, which is a +8. Then we move on to the last column. That's 1 by 0 here, which is a 0, plus -2 by -4, which is +8. All right, so we are done with the first row and the other column. Then we move on to the last row, which is 0, 1 versus the first column. So we're going to be 0 times -2, which is 0, plus 1 times -2, which is -2. Then we've got this row and this column, that's 0 times -4, which is 0, plus 1 times -4, which is -4. 0 times 0 here, that's 0, plus 1 times -4, which is -4. All right, now we can combine everything. Let us see what you're going to have. -2 plus 4, which is +2. -4 plus 8, this is going to give us +4. 0 plus 8, which is 8. 0 plus -2, that's -2. 0 plus -4, that's -4. 0 plus -4, which is -4 again. All right, so these are the coordinates that you're going to name our A1, our B1, and our C1. Okay, so we are going to take these coordinates, that is A1, 2, -2. B1, which is 4, -4, and C1, which is 8, -4. All right. So with these coordinates now, we are going to plot them on our graph, which is, let us take our graph here. That's A1, 2, -2. So I'm just going to quickly indicate these ones. A1, 2, -2, that's somewhere here. You mark your point. So that's A1 here. Okay, we said B1 is 4 - 4. Okay, so that is 4 - 4. 4 minus 4, which is somewhere here. All right, so that is 4 minus 4, you mark your point. And 8 minus 4, so this is B1. C1 is 8 minus 4, which is somewhere here. All right, so you mark your point, which is your C1. Okay, so let us join and see what our diagram is going to look like. If we just join these points here, we're going to have something like this. So you join A to A1, you're going to join also B to B1, B to C1, sorry, that is B to C1 here. All right, B to C1, then also A to C1, A1 to C1. Okay, so this is what you're going to do. All right, so join those points, you've got your image. So just like normal transformation, guys, you can see that it's a normal transformation, but let us cross-check what is happening. From A1 to B1, that side is not changed. It's only the only side that changed, or if you have to cross-check this one from A1 to C1. So we can't say this is enlargement. Enlargement is totally out. And also the question is not about describing to say what is the transformation. The question is for you to draw the image from the matrix that you are given. So take note about the question that you were given, guys. The question was for you to draw the image. So which means what you need is to have the question down. Okay, what is the question? Draw the image from which transformation. Okay, then you take your transformation. So that was x-axis variant shear factor -2. So you just need your matrix. All right, then the other one, draw and label the image of ABC under a shear. This time it's y-axis invariant shear factor -0,5. So we said when it is y-axis invariant, which means you're supposed to use this matrix, locate this one, 1K01. Okay, so we're going to use 1K01. So it's going to be like this, 1K. Okay, let me just use another ink here. So it's going to be 1K01. Whereby we are saying the y-axis is not moving. There's no movement. That is why you see it's a 0,1 like this. But the x-axis is the one that is being affected, and it's -0,5. So your matrix is going to be 1 minus 0,5, 0,1 like this. So this is the matrix that you're going to use. But knowing that the matrix by the object should give us the image. Okay, so I'm just going to do the calculations here. All right, so we need our matrix. That is matrix times object equal to image. And we said it's 1 minus 0,5, 0,1 times the object, which is ABC. Okay, so that is the object, which is ABC. So just like usual, the coordinates of ABC, we have got them, -2, our B, which is -4, our C, which was 0, -4. So row by column, just like what we did previously. So it's this row by the first column, second one, and third one, just like that. Okay, so let us start with the first one. 1 by -2, that's -2 plus 0 times -2, that's a 0. Okay, we move on to this column. So it's 1 by -4, which is -4 plus 0 by -4, that's a 0 there. 1 by 0, that's a 0 plus 0 by -4, which is 0. Okay, then we move on to this row now versus the first column. So it's -0,5 times -2. Negative gives us a positive. 0,5 times 2, that's a 1 plus 1 times -2, which is -2 there. All right, -0,5 times -4 is going to give us +2, plus 1 times -4, which is going to give us -4. Okay, -0,5 times 0 here, which is a 0, plus 1 times -4, which is -4. Okay, so you can add our terms here. That's -2 plus 0, which is -2, -4 plus 0, that's -4, 0 plus 0, that's a 0 there. Plus and minus, that's a minus, so it's 1 minus 2, of which 1 minus 2 is going to give us -1. Plus and minus is also a minus. 2 minus 4, that's -2. 0 plus -4, that's a minus. 0 minus 4, that is -4. Okay, so these are the coordinates of A2, B2, and C2. So all you need is to write them now as coordinates: -2, -1. We move on to B2, -4, -2, and C2, which is 0, -4. All right. So these are the coordinates that you're going to mark on your graph so that we can actually plot these points. All right. So let us quickly indicate these points. A -2, it was -2, -1. All right. -2, -1 somewhere here. So make sure that you mark your points properly. -2, -1, because this is 0, -2, -4, so which means -1 is somewhere here. So it's -2, -1 at this point. This is our A2. All right, then our B2, we say it is -4, -2, -4, -2 somewhere here. -4, -2, that's our B2. Then our C2, we said 0, -4. 0, -4 here. So it's actually the same point of C. It's a repetition, this one. So it's going to be your C2. So that one does not affect, actually. You just have to join the way that is given there. It doesn't actually affect. So this is what you're going to have. Okay, so let me insert a ruler so that we can join these ones. All right. So let us join these points A to B2, something like this. All right, we are just going to join these ones. That's something like this. Then we join from B2. I just join any point. As long as you've got these points, guys, it's just a matter of what? It's just a matter of joining them now, which is the best part. All right, so that's it. We can join this one and the last one from A2 to C2, like this. All right, let's just adjust this side a little bit, like this one. All right, so that's what you're going to have at the end. So here's just like that. Okay, so that's our triangle. So it depends with the triangle that you're given and how are you going to have it. But the idea there, whenever you're given a matrix, apply your matrix. Matrix times object is equal to the image. That is the whole idea. So as we can cross-check, guys, that is the whole part of a shear. Points, they move parallel to the invariant line. And whenever you're drawing the image, you need to know your matrix, okay? Matrix times object, you know that you obtain a, there's no need of you to subtract anything. As long you know your invariant line, then your matrix is there. That is the idea. Okay, so I want us to check this part here, which is on stretch. So stretch is divided into two. We've got the one-way stretch and the two-way stretch. So that is what we are given. And also, the object and the image, they are not the same, which means they are not isometries. For one-way stretch, it looks familiar like a shear. It looks familiar like shear, but there's a difference because this time points, they are going to move perpendicular to the invariant line. They are no longer parallel, they are perpendicular. Perpendicular meaning to say, when the points, they are moving, let's say, your x-axis is the invariant line. But when you join points, this is A, this is A1. When you join them, they are going to be perpendicular with the x-axis like this. They create 90 degrees. The way they move, they are going to be 90. But you saw that last time, A and A1 was moving like this. This was A, this was A1. The points, they were moving parallel to the invariant line, which means these lines, they will never meet. But under stretch, they are going to move perpendicular. So when they create 90 degrees, you know that one is a one-way stretch. Parallel to the invariant line, you know that one is it's a shear. So these are the differences that we are going to note between one-way stretch and shear. Of which two-way stretch, it is familiar, some familiars that we have with enlargement. The difference is that they are not going to be enlarged with the same scale factor. And that one I told you guys, this question for describing two-way stretch, actually, don't expect that one. You have to expect a question to use where you are using the matrix for shear to draw the image, not to describe. To describe that one, don't expect it to have it because actually to carry a lot of marks, but you just need to know its properties. I think that one can help. Okay, so I want us to see this part here. To describe one-way stretch, these are things that you're going to need. You state that is the one-way stretch, you state the invariant line, then you state the stretch factor. Okay, then for two-way stretch, there will be two now. It will be two-way stretch, which means you're going to have x-axis and y-axis invariant. Then each invariant line is going to have its own stretch factor. So you see, there are a lot of things that you're going to have, which means you need something like because to write this is 1 mark, this one 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 is one. So which means this question requires about 5 marks alone. So which means it's a lot of marks that you can have on under a two-way stretch. So mostly they ask you to draw the image using the matrix. But if you are to describe, these are the things that you're going to have. So it's a combination of both invariant lines, okay? Then the stretch factor, take note about the stretch factor is now different. The way that we used to calculate the shear factor, this one is distance of image from the, take note, it's from the invariant line over the object from the invariant line, which means you are taking your distance. Let's say this is your x-axis as your invariant line. The distances they are taken from the x-axis to the object, to the image, then also to the object. So it's a distance that you take, which is from that invariant line that you talked about before. Okay, so I'm going to explain later on, but these are things that you actually need for stretch. All right, then the matrices for stretch, we have got one-way stretch in the x-axis invariant. So using the look, so this one you can just use this mnemonic look this way. So it's 100k. That is x-axis invariant. Y-axis invariant is same thing. Look from this way. As you can see, it's a look from this way again. But this time we just use H because they are not the same. That is why I'm just using H001 like that. Then for two-way stretch, is going to be H00K, which you can take from what? From hook like this. You can just memorize using these mnemonics. All right, so, and the idea of matrix times object gives us image does not change. So this one, you're going to use it throughout. That one is not going to even change. So I hope this part is clear. Let us see how the questions can be given. The first one you're given, there's a triangle PQR, which has got vertices at P, Q, and R, which is draw and label the triangle, and also draw and label P1, Q1, R1 with the vertices at, that is the image. Then the question, describe the single transformation which maps triangle PQR onto triangle P1, Q1, R1. Okay, so that is the question. So I have already have the diagrams here, which is PQR and P1, Q1, R1. So from this part here, the thing that you're supposed to have is to know our invariant line. That is what you're going to have. So like I said, invariant line, you don't need to join all the lines. Okay, like if you are to cross-check PQ here, P1, Q, and they're actually in a straight line. If you are to join this one, they're going to create a straight line. So you can't get anything from there because it's a straight line. Also, from P to R here, and also P1, as you can see, they will be part of, they will never meet these lines. So we are going to join R to Q, R1 to Q, those ones they can join. So it's not about joining all the points. You join those ones that you know that they are going to meet, okay? So that's how you actually determine your invariant line. So from the diagram, we can think that it's enlargement. No, it's not enlargement because this side is not changed. P1 to Q1, it has not changed. Remember, enlargement, everything changed. But in this case, this side did not change, but PQ changed. So that is why we have to think of shear or one-way stretch. Okay, so that is the idea there. So I'm just going to extend this line a little bit so we see where it is going to be. All right, so let us just extend this one. If we extend it like this, okay, we extend also this one R to R1, that is R1 to Q1, this one. Let us extend this line like this. All right. So by extending these lines, you can see that these lines here, they meet here in the y-axis. So that means we have got our y-axis as the invariant line. So this is the first thing that you do to find the invariant line. So you know that the y-axis is the invariant line. Now, how are you going to see that it's a stretch or it's a shear? That is where now we said for shear, points, they move parallel to the invariant line. But for stretch, they are going to be perpendicular. So parallel, it's for shear. Perpendicular is for one-way stretch. Okay, so let us cross-check how these points are moving. Are they parallel or they are perpendicular? Okay, so this is the case. We said our y-axis is the invariant line. Okay, so this is how you test your points. You are saying if we are to put our y-axis the way that it is here, P here is moving to P1. I want us to see P is going to move to P1. And what is happening here? It is going to pass through the y. This is your y-axis. As you can see, P going to P1, it is creating 90 degrees. The same thing, R to R1, is it is moving, passing through the y-axis like this, it is creating 90 degrees. So which means these points, they're actually perpendicular, like the distance they are moving, they are perpendicular. So meaning to say from this direction that you are given, they are perpendicular. So if they are perpendicular, then it means we are having what? We are having a stretch. So we are going to describe now, it is a one-way stretch. It can be a two-way stretch because remember, two-way stretch, both they have to be invariant lines. Okay, so this one we are now describing, it is, okay, let us just write it properly here. So it is a one-way stretch. All right, so this is what you're going to have. Then already the invariant line is there because that's the first thing that you had to find, the invariant line. And you saw that your invariant line is your y-axis. So which means we have got y-axis invariant, that is invariant. Okay, then we need the stretch factor. Then I want you to cross-check, guys, properly on the stretch factor there. On the stretch factor, I want us to be very, very specific here. We said the stretch factor is the distance that is from the invariant line to the image. So we're going to start with this, guys. We said our invariant line is the y-axis. So we are going to say from the invariant line to the image, which is P1, over from the invariant line to P. That is how you take the distance from the invariant line to the image, from the invariant line to the object. Okay, so this is it. Let us go. This is our invariant line, which is our y-axis. So from the y-axis here to P1, what is the distance? And also the direction matters. As you are coming from the invariant line going to P, this is you're going to the what? To the positive. So you're going to calculate, this is your invariant line to P1. So it's going to be 2, 4, 6, 8. According to scale, it's 8. You move those boxes, but according to scale, those boxes, they represent 8. And also the direction, you are going to the positive in the x-axis like this, so it's a positive, okay? Then from the y-axis, which is your invariant line, to the object, which is P, how many units are you going to move? Okay, so we're going to start again from the y-axis here, going to P. As you can see, now we are going to the left, which means we are going to the negative. So it's going to be -2, -4. So this one, it's -4 according to scale, okay? So you're going to divide by -4. All right, so by dividing by -4, we are going to obtain -2. Okay, you do the same on Q, that is from the invariant line, which is the y-axis, to Q1, which is the image, from the same invariant line to Q, which is the, we must get the same answer. All right, so that is just a proof. This one, let us prove and see. Q from the invariant line is going to be 2, 4. These are 4 units from the y-axis. Going to Q1 is going to be 2, 4. So this one is 4 according to scale. We are going to the positive. So it's going to be a +4 over the invariant line to Q, which is the object, which is our Q. Okay, so this is our diagram here. It's going to be -2, just one box, it's -2. All right, so now if we are to divide 4, divide by -2, that one is a -2. So as you can see, it's one and the same thing. So I want you to prove this one. Are you going to get the same answer from the invariant line, which is the y-axis, to R1, over from the invariant line of y-axis to the object, which is R. I want you to prove if we are getting the same answer, we must have the same answer, which is -2. So which means our stretch factor is going to be -2. So that's how you simply have the stretch factor. The stretch factor is simply the distance from the invariant line to the image, from the invariant line to the object. So that is the idea. So I think for one-way stretch is direct. The other pair or the other type of a question now is going to be on the matrix concept. Like I said, you can be given matrices like this one. They are given A, B, C with vertices A, B, and C. Draw and label the images of A, B, C under the following transformation. The first one is a one-way stretch of factor 2 x-axis invariant. So we're going to use the matrix concept. that is matrix times object is equal to image. But this one, it's x-axis invariant. So we're going to use our look concept. Remember the look concept. So it's going to be look like this, okay? Or it can be look like this. All right, that is look. We have got a 0 here. Another, so it's going to be like this. So it's going to be look like this, okay? So these are the two matrices, but which one is for the x-axis invariant, which means there's no movement in the x-axis? So the one for the x-axis invariant, let us cross-check. Here is this one. There is no movement in the x-axis, which means x is 1 is 0. This one, there is no movement, so it's going to be this one. All right, so using our matrix is going to be matrix times object. Now our k, which is the stretch vector, is 2. That is your stretch vector 2. So which means your matrix is going to be 1, 0, 0, 2, like this. So this is your matrix. So matrix times object should give us the image, just like that. So that is it. You write your object, which is minus 2, minus 4, minus 2, B, which is minus 2, and our C, which is minus 2, 4. So that will be negative 2, 4. Negative 4, 2, or negative 2, 4. This is negative 4, 2. All right, so that's negative 4, 2. So this is your PQR. Oh, it's ABC actually. This is ABC. Okay, this is another question. So it's ABC. So I'm just going to name these points A, B, C. Then we can perform our matrix multiplication row by column. It's going to be this part and this column, and this column. Okay, so that's 1 by negative 4, which is negative 4 plus 0. Negative 2 plus 0 here. 1 times negative 4. That's negative 4 plus 0 again. You move on to this row. First column, 0 by negative 4, that is 0 plus 2 times minus 2, that is minus 4. 0 times 2, minus 2, that's a 0, plus 2 times minus 2, which is minus 4. 0 times minus 4, that's a 0 here, plus 2 times 2, which is 4. All right, so you can add whatever that you're going to have here. So that's negative 2 plus 0 there, which is minus 4 plus 0, which is minus 4, minus 2 plus 0, which is minus 2, minus 4, 0 plus minus 2, which is minus 2, 0 plus minus 4, which is minus 4, and 4. Okay, so these are the coordinates, which means we've got A1, B1, C1. But you're supposed to write these as coordinates now. All right, so you're supposed to write these as coordinates, which means we are saying that A1 is negative 4, negative 2. B1 is, we are going to have our B1 here, which is negative 2, negative 4, and our C1, which is negative 4, 4. Okay, so these are the coordinates that you're going to have. And with these coordinates, we are supposed to mark them, draw the object. Okay, so this one I'm not going to waste much time working on it, drawing the object, but these are the coordinates that you're going to use. Okay, so let us cross-check on this one, the item 2. So this is a condition that you're going to have on a two-way stretch. Mostly the question will be like this. You want to draw the image under a two-way stretch of vector 2 parallel to the x-axis and the stretch vector 3 parallel to the y-axis. Okay, so remember we say the matrix for two-way stretch enlargement is hook. Okay, so this is your hook here. So how do I take this matrix is very, very important. If you are given like this one, stretch vector 2 parallel to the x-axis, which means it is going to affect the x-axis part, which means the x-axis is the one that is got h. So it's parallel, which means your h here is going to be having what? The 2 on your h. It's parallel to the x. This is your x, this is your y. So parallel to the x-axis, which means it's affecting the x-axis. So it's going to be 2, 0. Parallel to the y-axis, which is this one, is going to be 0, 3. Okay, so this is your matrix. So matrix times object should give us the image. Okay, so I'm saying this matrix that we have, we multiply to the object now. Matrix times object, or object, we take it as it is. It was A, B, C, which is minus 4, minus 2, minus 2, minus 2, minus 4, 2. So that's it, guys. You multiply everything. So you're going to obtain something like -8, -4, -8, -6, -6, 6. Okay, so this will be your A2, B2, C2. So you just do your normal matrix multiplication. These are the answers, all right, that you're going to get, which is -8, -6 as your A2, your B2 as your -4, -6, and your C2 as your -8, 6. So from there, you draw these points on your graph. So here I have the presentation of the object. This was your object. Then you draw your images. That will be done. So if you are dealing with transformation, guys, that is the whole part that you're going to have under transformation, shear and stretch. For one-way stretch, revise shear and one-way stretch. The basics of shear and one-way stretch are the ones that you're supposed to know. So I think with this information, guys, it's clear. You can do as much questions as possible, revise as much questions from question papers now. Now is the right time for you to revise question papers. So I shall explain more from question papers, but the basic part of just having a shear and a stretch, these are the basics. So that's it, guys, from Zone African Motives, working on O-level mathematics revisions and also past exam papers till we meet again.